Hello friends, in the previous lecture we learned that a charged particle sets up an electric field in the surrounding space. If a second charged particle is located in that space, an electrostatic force acts on it due to the magnitude and direction of the field at its location. Then we learned that electric field lines originate on positive charges and terminate on negative charges. And finally, we learned that if more than one charged particle sets up an electric field at a point, the net electric field is the vector sum of the individual electric fields. That is, electric fields obey the superposition principle. In today's lecture, the learning objectives would be to discuss the electric field due to a dipole, the electric field due to a line of charge, and the electric field due to a charged disk. The electric field due to an electric dipole. After going through this module, you should be able to draw an electric dipole, identify the charges, dipole axis and direction of the electric dipole moment. Identify the direction of the electric field at any given point along the dipole axis, including between the charges. Outline how the equation for the electric field due to an electric dipole is derived from the equations for the electric field due to the individual charged particles that form the dipole. For a single charged particle and an electric dipole, compare the rate at which the electric field magnitude decreases with the increase in distance. That is, identify which drops off faster. Figure shows the pattern of the electric field lines for two particles that have the same charge magnitude q but opposite signs. A very common and important arrangement known as the electric dipole. The particles are separated by distance d and lie along the dipole axis, an axis of symmetry around which you can imagine rotating the pattern. Let's label that axis as a z axis. Here we restrict our interest to the magnitude and direction of the electric field at an arbitrary point P along the dipole axis at a distance z from the dipole's midpoint. Figure shows the electric fields set up at P by each particle. The nearer particle with charge plus q sets up field E positive in the positive direction of the z axis, that is directly away from the particle. The farther particle with charge minus q sets up a smaller field E negative in the negative direction, that is directly towards the particle. We want the net field at P, which is given by this equation derived from the principle of superposition of electric field, that is E is equal to E1 plus E2 plus E3 and so on up to En. However, because the field vectors are along the same axis, let's simply indicate the vector directions with plus and minus signs, as we commonly do with forces along a single axis. Then we can write the magnitude of the net field at P as E is equal to E positive minus E negative, which is equal to 1 upon 4 pi epsilon 0 into q upon r square positive minus 1 upon 4 pi epsilon 0 into q upon r square negative, which is again equal to q upon 4 pi epsilon 0 into z minus half d whole squared minus q upon 4 pi epsilon 0 into z plus half d whole squared. After a little algebra, we can rewrite this equation as E is equal to q upon 4 pi epsilon 0 z square into 1 upon 1 minus d upon 2z whole squared minus 1 upon 1 plus d upon 2z whole squared. After forming a common denominator and multiplying its terms, we come to this equation. We are usually interested in the electric field of a dipole only at a distance that are larger compared with the dimensions of the dipole, that is, at distances such that z is much greater than d. At such large distances, we have d upon 2z much less than 1 in this equation. Thus, in our approximation, we can neglect the d upon 2z term in the denominator, which leaves us with E is equal to 1 upon 2 pi epsilon 0 into qd divided by z cube. The product qd, which involves two intrinsic properties q and d of the dipole, is the magnitude p of a vector quantity known as the electric dipole moment. Thus, we can write equation A as E is equal to 1 upon 2 pi epsilon 0 into p upon z cube. The direction of p is taken to be from the negative to the positive end of the dipole as indicated. We can use the direction of p to specify the orientation of a dipole. Equation B shows that if we measure the electric field of a dipole only at distant points, we can never find q and d separately. Instead, we can find only their product. The field at distant points would be unchanged if, for example, q were doubled and d simultaneously halved. Although equation B holds only for distant points along the dipole axis, it turns out that E for a dipole varies as 1 upon r cube for all distant points, regardless of whether they lie on the dipole axis. Here r is the distance between the point in question and the dipole center. Inspection of these two figures shows that the direction of electric field for distant points on the dipole axis is always the direction of the dipole moment vector p. This is true whether point P in figure A is on the upper or the lower part of the dipole axis. Inspection of equation B shows that if you double the distance of a point from a dipole, the electric field at that point drops by a factor of 8. If you double the distance from a single point charge, however, the electric field drops only by a factor of 4. Thus, the electric field of a dipole decreases more rapidly with distance than does the electric field of a single charge. The physical reason for this rapid decrease in electric field for a dipole is that from distant points a dipole looks like two particles that almost but not quite coincide. Thus, because they have charges of equal magnitude but opposite signs, their electric fields at distant points almost but not quite cancel each other. Electric field due to a line of charge. After going through this module, you should be able to find the linear charge density for charge along a line, the surface charge density for charge on a surface, and the volume charge density for charge in a volume. Find the net electric field at a given point near the line, and finally explain how symmetry can be used to simplify the calculation of the electric field at a point near the line of uniformly distributed charge. Procedure to find electric field from line charges. So far, we have dealt only with charged particles. A single particle or a simple collection of them We now turn to much more challenging situation in which a thin, approximately one-dimensional object such as a rod or ring is charged with a huge number of particles, more than we could ever even count. Many learners consider this module to be the most difficult for a variety of reasons. There are lots of steps to take, a lot of vector features to keep track of, and after all that we set up and then solve an integral. The worst part, however, is that the procedure can be different for different arrangements of the charge. Here, as we focus on a particular arrangement, that is a charged ring, be aware of the general approach so that you can tackle other arrangements such as rods and partial circles. Figure here shows a thin ring of radius r with a uniform distribution of positive charge along its circumference. It is made of plastic, which means that the charge is fixed in place. The ring is surrounded by a pattern of electric field lines. But here we restrict our interest to an arbitrary point P on the central axis. Central axis means the axis through the ring's center and perpendicular to the plane of the ring at distance z from the center point. The charge of an extended object is often conveyed in terms of a charge density rather than the total charge. For a line of charge, we use the linear charge density, that is the charge per unit length, with the SI unit of coulomb per meter. So far, we have an equation for the electric field of a particle. We can combine the field of several particles as we did for the electric dipole to generate a special equation, but we are still basically using the magnitude equation of point charge. Now take a look at the ring. That clearly is not a particle, and so magnitude equation of point charge does not apply. So what do? The answer is to mentally divide the ring into differential elements of charge that are so small that we can treat them as though they are particles. Then we can apply magnitude equation of point charge. We now apply magnitude equation of point charge to each charge element dq. The front d emphasizes that the charge is very small and can write an expression for its contribution of electric field dE. The front d here emphasizes the contribution is very small. However, each such contributed field vector at P is in its own direction. How can we add them to get the net field at P? The answer is to split the vectors into components and then separately sum one set of components and then the other set. However, first we check to see if one set simply cancels out. We now have a huge number of dq elements in the ring and thus a huge number of dE components to add up, even if we cancel out one set of components. So how can we add up more components than we could even count? The answer is to add them by means of integration. So guys, this is the procedure to be followed while solving such problems. Electric charge from a ring. Let's do all we have discussed in the previous section, but again be aware of the general procedure, not just the fine details. We randomly pick the charge element shown in figure. Let ds be the arc length of the dq element. Then in terms of the linear density, we have dq is equal to lambda ds. Here lambda is the linear density. This charge element sets up the differential electric field at P at distance r from the element. Next, we rewrite the magnitude equation of point charge in terms of our new symbols dE and dQ, but then we replace dQ using equation d. Thus, the field magnitude due to the charge element is dE is equal to 1 upon 4 pi epsilon 0 into dQ upon r square, which is equal to 1 upon 4 pi epsilon 0 into lambda ds upon r square. Notice that the symbol r is the hypotenuse of the right triangle. Thus, we can replace r by rewriting above equation as dE is equal to 1 upon 4 pi epsilon 0 into lambda ds divided by z square plus r square. Because every charge element has the same charge and the same distance from point P, equation E gives the field magnitude contributed by each of them, and the figure tells us that each contributed dE leans at an angle theta to the central axis, that is the z axis, and thus has components perpendicular and parallel to that axis. Now comes the neat part, where we eliminate one set of those components. In figure, consider the charge element on the opposite side of the ring. It too contributes the field magnitude dE, but the field vector leans at an angle theta in the opposite direction from the vector from our first charge element, as indicated in the side view of this figure. Thus, the two perpendicular components cancel. All around the ring, this cancellation occurs for every charge element and its symmetrical partner on the opposite side of the ring. So we can neglect all the perpendicular components. Now notice that all the remaining components are in the positive direction of the z axis. So we can just add them up as scalars. Thus, we can already tell the direction of the net electric field at P, that is directly away from the ring. From figure, we see that the parallel components each have magnitude dE cos theta. We can replace cos theta using the right triangle in figure to write cos theta is equal to z upon r and is equal to z upon z square plus r square to the power half. Multiplying equation E by equation F gives us the parallel field component from each charge element as dE cos theta is equal to 1 upon 4 pi epsilon 0 into z lambda divided by z square plus r square to the power 3 by 2 into ds. Because we must sum a huge number of these components, we set up an integral that moves along the ring from element to element from a starting point, call it s is equal to 0, through the full circumference, that is s is equal to 2 pi r. Only the quantity s varies as we go through the elements. The other symbols in equation G remain the same. So we move them outside the integral and find E is equal to integral of dE cos theta, which is equal to z lambda upon 4 pi epsilon 0 into z square plus r square to the power 3 by 2 into integral of ds from 0 to 2 pi r, which comes out to be z lambda into 2 pi r divided by 4 pi epsilon 0 into z square plus r square to the power 3 by 2. This is a fine answer, but we can also switch to the total charge by using lambda is equal to q upon 2 pi r and get E is equal to qz divided by 4 pi epsilon 0 into z square plus r square to the power 3 by 2. If the charge on the ring is negative instead of positive as we have assumed, the magnitude of the field at P is still given by this equation. However, the electric field vector then points towards the ring instead of away from it. Conclusion. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. An electric dipole consists of two particles with charges of equal magnitude q but opposite signs, separated by a small distance d. The electric dipole moment P has magnitude qd and points from the negative charge to the positive charge. Because of the I upon z cube dependence, the field magnitude of an electric dipole decreases more rapidly with distance than the field magnitude of either of the individual charges forming the dipole, which depends on 1 upon r square. The equation for the electric field set up by a particle does not apply to an extended object with charge. So friends, that is it for today. See you in the next lecture, where we shall consider two-dimensional objects such as a disk with charge spread over a surface, and then talk about point charge in an electric field. Thank you very much.